approximate visualization of the frequency response HTL.j omega of a system. So it consists of straight line segments that are constructed based on the asymptotic properties of HTL.j omega. So in the body diagrams, we will have a magnitude plot and a phase plot. In order to construct the body diagram of a system, we have to learn the body diagrams of the basic systems. So there are 6 basic systems we have learned in the last class: the DC gain, the differentiator, the integrator, the zero factor, the pole factor, and the second order factor. So first, let's look at the body diagrams of the DC gain. So this is the magnitude plot, and this is the phase plot. We can see that for the DC gain, the magnitude plot is a constant, which is equal to 20 times log 10 of kdc, and the phase plot is also a constant, which is equal to 0 degrees. And then for the body plots of the differentiator, the magnitude plot is a straight line with slope equal to plus 20 dB per decade, and the phase is a constant, which is equal to 90 degrees. And then we look at the integrator. So for the integrator, the magnitude plot is a straight line with slope equal to minus 20 dB per decade, and the phase is equal to minus 90 degrees. Then for the zero factor, in the magnitude plot, at low frequency, the magnitude is equal to 0 dB, and then there is a slope change located at omega equal to Zm. After that, the slope of the straight line is equal to plus 20 dB per decade. As for the phase plot, when the frequency is below Zm over 10, the phase is equal to 0 degrees, and when the frequency is higher than 10 Zm, the phase is equal to 90 degrees. And in between, we can just connect these 2 points, and then we look at the pole factor. So when the frequency is less than Pn, the magnitude is equal to 0 dB. When the frequency is larger than Pn, the slope of the straight line is equal to minus 20 dB per decade. When the frequency is below Pn over 10, the phase is equal to 0 degrees, and when the frequency is larger than 10 Pn, the phase is equal to minus 90 degrees. And in between, we will connect these 2 points. The last case is the second order factor. So for the second order factor, the standard form of the transfer function is given by HTL.s of HTL.s equal to omega n square over s square plus 2 theta omega n s plus omega n square. So here we only discuss the case when theta is larger than or equal to 0, less than or equal to 1. In this case, the magnitude plot, this is the magnitude plot. When the frequency is less than omega n, the magnitude is equal to 0 dB, and when the frequency is larger than omega n, the slope of the straight line is equal to minus 40 dB per decade. In the phase plot, when the frequency is less than 0.1 omega n, the phase is equal to 0 degrees, and when the frequency is larger than 10 omega n, the phase is equal to minus 180 degrees. So we've learned the body diagrams of the basic systems, and we are able to plot the body diagrams of a specific system. So in this class, we are going to learn how can we derive the corresponding transfer function from the body magnitude plot. Okay, so before we learn how to derive the transfer function from the body plots, we are going to summarize the basic systems. Okay, so first, let's look at the low frequency asymptote. Okay, so we have 6 basic systems. First one is kdc. Second one is the differentiator, which is kd multiplied by s. Third one is ki multiplied by 1 over s. Fourth one is the zero factor, which is s over zm plus 1. Fifth one is the pole factor, which is 1 over s over pn plus 1. Sixth one is the second order factor, which is omega n squared divided by s squared plus 2 theta omega n s plus omega n squared. So according to the transfer function, we will be able to write out the frequency response. For the first one, it is still kdc. Second one is kd multiplied by j omega. Third one is ki multiplied by 1 over j omega. Fourth one is j omega over zm plus 1. Fifth one is 1 over j omega over pn plus 1. The last one is omega n squared over minus omega squared plus 2j theta omega n omega plus omega n squared. So now we are going to look at the corresponding slope, which is dB per decade, and the magnitude at low frequency. So for the DC gain, it is equal to 0 dB per decade, and then for the magnitude in dB, it is equal to 20 times log 10 of kdc, and then for the slope of the differentiator, it is equal to plus 20 dB per decade. As for the magnitude in dB, according to this expression here, it will be equal to 20 times log 10 of kd multiplied by omega. So it is equal to 20 times log 10 of kd plus 20 times log 10 of omega. Now for the third one, which is an integrator, the slope is equal to minus 20 dB per decade, and at low frequency, the corresponding frequency response can be approximated as 1 because the magnitude of the first term will be very small since omega is much less than Zm. So the first term can be neglected, therefore it can be approximated as 1. So in this case, at low frequency, the slope of it will be equal to 0, and the magnitude of it will also be equal to 0 dB. And then for the pole factor, when the frequency is very low, omega will be much less than Pn, therefore the magnitude will also be equal to 0 dB. And then we look at the second order factor. So at low frequency, omega will be much less than omega n, which means the first 2 terms in the denominator can be neglected. If the first 2 terms in the denominator are neglected, then this term will be equal to omega n squared over omega n squared, which is approximately equal to 1. Therefore, the slope is equal to 0 dB per decade, and the magnitude is equal to 0 dB. Therefore, when the frequency is very low, we cannot see the existence of the zero factor. We are also not able to see the existence of the pole factor and the second order factor. At low frequency, we are only able to see the existence of the DC gain, the differentiator, and the integrator. So now let's look at the first step of the derivation. So in the first step, by examining the slope of integrator. So now let's look at the first step of the derivation. So in the first step, by examining the slope of the low frequency asymptote of the body magnitude plot, if the slope is equal to plus 20 Okay, So if the slope is equal to plus 20L, we can see that when the slope is positive, we can only have the differentiators. So it means that there is a cascade of L identical differentiators, of which the transfer function is given by KD times S to the power of L. And then in this case, the magnitude in dB will be equal to 20L times log 10 of KD plus 20L times log 10 of omega, which is 10 multiplied by this term here. Okay, now we look at the second case. In the second case, the slope is equal to minus 20L dB per decade. Since here the slope is negative, so we will only have the integrators. So the integrators, for the integrators, one integrator will be corresponding to the slope equal to minus 20 dB per decade. Since the slope here is equal to minus 20 times L dB per decade, therefore we will have a cascade of L identical integrators, of which the transfer function is given by Ki over S to the power of L. And then the magnitude in dB will be equal to L multiplied by this expression here. Therefore the magnitude in dB will be equal to 20L times log 10 of Ki minus 20L times log 10 of omega. And then in the last case, if the slope is equal to 0 dB per decade, it means that we do not have the differentiator or integrators. We will only have the DC gain. So the corresponding magnitude will be equal to 20 times log 10 of KDC. Okay, so this is what we do when we examine the slope of the low frequency asymptote. Now we proceed to look at the slope change. Okay, so the second step is to check the slope change. Okay, so now let's proceed to see the slope change. Again, we will look at the 6 subsystems. So the first subsystem is again the DC gain. The second subsystem is the differentiator, which is KD multiplied by S. The third subsystem is KI multiplied by 1 over S. And the fourth subsystem, it is the zero factor, which is S over Zm plus 1. And the fifth subsystem is the pole factor, which is 1 over S over Pn plus 1. And the sixth subsystem is the second order factor, which is omega n squared over S squared plus 2 theta omega ns plus omega n squared. Okay, so now we are also going to look at the frequency response of these 6 subsystems. For the first one, the frequency response is again equal to KDC. Second one is KD multiplied by J omega. Third one is KI multiplied by 1 over J omega. And the fourth one is J omega over Zm plus 1. The fifth one is 1 over J omega over Pn plus 1. And the last one is omega n squared over minus omega squared plus 2 theta omega n multiplied by J omega plus omega n squared. So now we will look at the slope change in dB per decade. Okay. First, we need to know what is a slope change. So if we look at the body diagram here, so this is the magnitude plot of a second order system. So here we will have a slope change at omega n. The slope change is equal to minus 40 dB per decade, because when omega is less than omega n, the slope is equal to 0 dB per decade. And when omega is larger than omega n, the slope is equal to minus 40 dB per decade. Therefore, the slope change is equal to minus 40 dB per decade minus 0 dB per decade, which is equal to minus 40 dB per decade. Okay, so this is called a slope change. Okay, so now we look at the slope change of the subsystems one by one. So for the first one, the DC gain, there is no slope change. So the slope change is equal to 0 dB. And then for the differentiator, since the differentiator is a straight line with slope always equal to plus 20 dB per decade, so there is no slope change. It is equal to 0 dB per decade. For the third subsystem, it is an integrator. For the integrator, the slope is always equal to minus 20 dB per decade. So there is also no slope change. It is equal to 0. And then for the zero factor, there is a slope change located at omega equal to Zm. And the slope change is equal to plus 20 dB per decade. And then we look at the pole factor. So for the pole factor, we also have a slope change located at Pn, and the slope change is equal to minus 20 dB per decade. And then for the second order subsystem, the slope change is located at omega n, which is equal to minus 40 dB per decade. So we can see that from the slope change, we will not be able to see the existence of the DC gain. We will not be able to see the existence of the differentiator, and also we will not be able to see the existence of the integrator, but we will be able to see the zero factor, the pole factor, and the second order factor. So now let's look at this step. According to the slope change, what can we conclude? So if the slope change is equal to plus 20L, and the slope change is located at omega equal to omega naught, then What does it mean? If the slope change is positive, then we can only have the zero factors because only the slope change for the zero factor is positive. So it means that we will have a cascade of L identical zero factors, of which the transfer function is equal to S over omega naught plus 1 to the power of L. Okay. So if the slope change is positive and its slope change is equal to plus 20 L dB per decade, then it means that we have a cascade of L identical zero factors, of which the transfer function is equal to S over omega naught plus 1 to the power of L. And then if we have the slope change equal to minus 20 dB per decade, and it happens at omega equal to omega naught. So if L is equal to 1, it means that the slope change is minus 20 dB per decade. If the slope change is equal to minus 20 dB per decade, from this table, we know that it should be a pole factor. So it should be a pole factor with transfer function equal to 1 over S over omega naught plus 1. And then if L is equal to 2, then the slope change is minus 40 dB per decade. Then there are two cases. The first case is that we will have a repeated pole factor, of which the transfer function is equal to 1 over S over omega naught plus 1 to the power of 2. Or we could also have a second order factor. So the transfer function of the second order factor is omega naught squared over S squared plus 2 theta omega naught S plus omega naught squared. It should be noted that for the second order factor, theta should be larger than or equal to 0, less than or equal to 1. Okay. Then if L is larger than 2, then we may have a hybrid of pole factors and second order factors. So in this case, the transfer function will be equal to 1 over S over omega naught plus 1 to the power of P times omega naught squared over S squared plus 2 theta omega naught S plus omega naught squared to the power of Q, where P plus 2Q is equal to L. So in this case, we could also have P equal to 0 or Q equal to 0. Now we can look at this example here. Okay, so let's look at the example 8-4. The Bode magnitude of an LTI system with the following transfer function is shown below. We need to identify the value of A, B, omega n, and k, and we also need to find out the high and low frequency asymptotic values of the phase response. Okay, so first let's do question A. Okay, so from this magnitude plot, we know that at low frequency, the slope is equal to plus 20 dB per decade, which means the slope here is equal to plus 20 dB per decade, and it cuts the point here, which is 0.1 and 0 dB. Okay, so what does it mean if the slope is equal to plus 20 dB per decade? It means that we will have a differentiator, KD multiplied by S. And then how can we calculate KD? In order to calculate KD, we need to use this point here. So this it cuts this point. It means that 20 times log 10 of KD multiplied by 0.1 is equal to 0, which means KD multiplied by 0.1 is equal to 1. Therefore, KD is equal to 10. So at low frequency, we will have a differentiator of which the transfer function is given by 10 multiplied by S. Okay, now we look at the slope change. We have two slope change. We look at the first slope change. So the first slope change happens at, here is 0.1, 0.2, 0.3, 0.4. So this point is 0.5. Okay, so it is located at 0.5 radians per second. Okay, maybe I label it 0.2, 0.3, and this is 0.4. Okay, and the slope change is equal to minus 20 dB per decade, because when the angular frequency omega is less than 0.5, the slope is equal to plus 20 dB per decade, and when the angular frequency is larger than 0.5, the slope is equal to 0 dB per decade. Therefore, the slope change is equal to 0 minus 20, which is minus 20 dB per decade. Okay, since the slope change is equal to minus 20 dB per decade, then we can only have a pole factor. So the pole factor will be 1 over S over Pn plus 1, and since the slope change is located at 0.5, so the expression should be 1 over S over 0.5 plus 1. Okay, so this is corresponding to the first slope change. Now let's look at the second slope change. The second slope change is here. So for this point, it is equal to, so since this point here is 1, so this should be 2. It is located at 2 radians per second. And what is the slope change here? So the slope change here is minus 40 dB per decade. Since the slope change is equal to minus 40 dB per decade, it can either be 2 pole factors or 1 second order factor. And since we have the resonance here, which is shown here using the orange line here, so it should be a second order factor. Since we have the resonance here, so it should be a second order factor. So if we have the second order factor, the transfer function is given by omega n squared over S squared plus 2 theta omega n S plus omega n squared. And since the slope change happens at 2 radians per second, so omega n should be equal to 2, then the transfer function will be equal to 4 divided by S squared plus 4 theta S plus 4. Okay, so then we need to cascade all the subsystems. So if we cascade all the subsystems, then we will have 10S multiplied by 1 over S over 0.5 plus 1 multiplied by 4 over S squared plus 4 theta S plus 4. And then we simplify this expression, then we will have 40 multiplied by S over 0.5 plus 1 multiplied by S squared plus 4 theta S plus 4. Okay, if we compare this expression with this expression here, we will find that K is equal to 40, A is equal to 0, B is equal to 0.5. and omega n is equal to 2. Okay, so now we will proceed to solve the second sub-question. What are the high frequency and low frequency asymptotic value of the phase response? Okay, so in question B, at low frequency, what will be the phase response? So at low frequency, we only need to consider the number of the integrators minus the number of the differentiators multiplied by minus 90 degrees. So what is the number of integrators here? So we do not have integrators. And what is the number of differentiators? So we have one differentiator multiplied by minus 90 degrees. So at low frequency, the asymptotic phase response is equal to 90 degrees. And then at high frequency, we need to use the number of poles minus the number of zeros multiplied by minus 90 degrees. So what is the number of poles? So here we have 1 plus 2, so it is 3 poles, and then we have 1 0. So we have 3 minus 1 multiplied by minus 90 degrees. So at high frequency, the asymptotic phase response is equal to minus 180 degrees. Okay, so that's all for chapter eight. 3 minus 1 multiplied by minus 90 degrees. So at high frequency, the asymptotic phase response is equal to minus 180 degrees. Okay, so that's all for chapter 8. Okay, so now let's look at the tutorial questions. So let's look at tutorial 6 first. Okay, in tutorial 6, for the following systems, determine the order of the system and the pole zero axis. Sketch the pole zero map. So here for question 1, pole zero axis, sketch the pole zero map. So here, since the order of the poles is equal to 3, so it is a third order system. And then for the pole zero axis, it is equal to the number of poles, which is 3, subtract minus the number of zeros, which is 2, so it is equal to 1. And then we need to sketch the pole zero map. In order to sketch the pole zero map, we need to rewrite the transfer function. So in this case, the numerator can be written as 1, s plus 1 multiplied by s plus 0.5, and the denominator can be written as s multiplied by s plus 0.6j multiplied by s minus 0.6j. Okay, so in the pole zero map, we will use circle to represent the zeros. So one of the zeros is at minus 1, another zero is at minus 0.5, and the 3 pole factors are located on the imaginary axis. Okay, so one pole is here, which is equal to 0.6j, one pole is here, which is equal to 0, and another pole is here, which is equal to minus 0.6j. This is for the first question here. Now we look at question B. H2TL.s is equal to 1 minus 2s over s 0.5s plus 0.75 square multiplied by 2s plus 1. So again, this system is a third order system. And then the pole 0 axis will be equal to 3 minus 1, which is equal to 2. Okay, so the pole 0 axis is equal to 2. And then to sketch the pole 0 map, we need to rewrite this transfer function. H2TL.s, it is equal to minus 2 s over minus 2 times s minus 0.5 divided by 0.5 square multiplied by 2 multiplied by s plus 1.5 multiplied by s plus 1.5 multiplied by s plus 0.5. Okay, so here in the pole 0 map, we have 1 0, it is located at 0.5, and we have 3 poles. The 3 poles, 2 of them are located at minus 1.5. One of them is located at minus 0.5. Now we look at the third question here. So here we have h3 TLR s equal to 40s squared over s plus 6 times s squared plus 8s plus 25. Again, it is a third order system. Okay, and then the pole zero axis is equal to 3 minus 2, which is equal to 1. And then in order to plot the pole zero map, we need to rewrite the transfer function. So here we have 40 multiplied by s multiplied by s. And then in the denominator, we have s plus 6 multiplied by s plus 4 plus 3j multiplied by s plus 4 minus 3j. Therefore, on the pole zero map, we will have 2 zeros here, and then we will have 3 poles. One pole is located at s equal to minus 6 plus 3j, and minus 4 minus 3j. Okay. Now we can proceed to look at question 2. For the following linear time invariant continuous time systems, determine if the system is stable, marginally stable, or unstable. So first, let's look at the first question. Impulse response is ht equal to e to the power of minus t plus e to the power of 2t times ut. So for this question, we can see that as t tends to infinity, ht will tend to infinity. So this system is unstable. And then we look at question B. Impulse response is ht equal to sine 2t times ut. So we can see that as t tends to infinity, ht oscillates. Since it does not converge to 0 and also not blow up, so it is called marginally stable. Now we look at the third question. Impulse response is ht equal to e to the power of minus t times sine 2t times ut. As t tends to infinity, ht will tend to 0. So it is a stable system. And then we look at question D. The transfer function is equal to s plus 9 over s squared plus 9. So in this case, the transfer function can be written as s plus 9 over s plus 3j multiplied by s minus 3j. So for these systems, the poles are equal to plus or minus 3j, which are located on the imaginary axis. Since the poles are located on the imaginary axis, so it should be marginally stable. And then we look at question E. The transfer function is h tilde s equal to 4 over s squared plus 4 squared. So in this case, the transfer function can be written as 4 over s plus 2j multiplied by s plus 2j multiplied by s minus 2j multiplied by s minus 2j. So we have poles equal to minus 2j plus 2j plus 2j. Since we have repeated poles located on the imaginary axis, so it is marginally stable. Oh, it is unstable, sorry, it is unstable. And then we look at question F. The transfer function is h tilde s equal to 1 minus 2s over s squared plus 2s plus 5. Okay, so in this case, we still need to rewrite the transfer function. It is 1 minus 2s over s plus 1 square plus 2 square. So it is equal to 1 minus 2s over s plus 1 plus 2j multiplied by s plus 1 minus 2j. So we can see the two poles are minus 1 minus 2j and minus 1 plus 2j. The two poles are located on the left half of the S-plane. So the system is stable. Okay, then we look at the question G. So here, I will multiply everything by ut here. So here, yt, this expression is multiplied by ut, and xt, it is also multiplied by ut. Okay, so here, let's solve this question together. So we have yt equal to 2t minus 2 over 5 plus 2 over 5 e to the power of minus 5t multiplied by ut. So in this case, if we apply the Laplace transform, then we will have 2s 2 multiplied by 1 over s squared minus 2 over 5 multiplied by 1 over s. Plus 2 over 5 multiplied by 1 over s plus 5 multiplied. Okay, then we look at the question G. So here, I will multiply everything by ut here. So here, yt, this expression is multiplied by ut, and xt, it is also multiplied by ut. Okay, so here, let's solve this question together. So we have yt equal to 2t minus 2 over 5 plus 2 over 5 e to the power of minus 5t multiplied by ut. So in this case, if we apply the Laplace transform, then we will have 2s 2 multiplied by 1 over s squared minus 2 over 5 multiplied by 1 over s plus 2 over 5 multiplied by 1 over s plus 5. So this is the Laplace transform of the output. As for the input, xt, it is equal to t times ut. Therefore, xtr dot s will be equal to 1 over s squared. So in order to derive the transfer function will be equal to ytr dot s divided by xtr dot s. So in this case, what do we have here? So we will have s squared multiplied by 2 over s squared minus 2 over 5 multiplied by s 1 over s plus 2 over 5 multiplied by 1 over s plus 5. So we will have 2 minus 2 over 5 multiplied by s plus 2 over 5 multiplied by s squared over s plus 5. And then we can further simplify this expression. So it will be 2 minus 2 over 5s plus 2 over 5 multiplied by s squared minus 25 plus 25 over s plus 5. So it is 2 minus 2 over 5s plus 2 over 5 multiplied by, so s minus 25. Over s plus 5, it is s minus 5. And then we will have plus 2 times 25 over 5, it is equal to 10 over s plus 5. So the first two terms here, if we sum them, if we do the summation, it is equal to 0. So as a result, the transfer function is equal to 10 over s plus 5. So the pole is equal to minus 5, which means the system is stable. Now we can look at Q3. So here HTL.S is equal to K over ST plus 1. XT is equal to, here I will need to multiply this expression by UT. Okay, and then YT is the corresponding system output. We need to find an expression of YT in terms of K and T. Okay, so let's do it here. So for Q3, we know that HTL.S is equal to K over ST plus 1, and XT is equal to 0.4 plus 2 times sine 0.25t multiplied by UT. So in order to derive the expression for YT at steady state, we need to figure out the frequency components of xt. So for this term of xt, the corresponding angular frequency is equal to 0. And for the second term here, the corresponding angular frequency is equal to 0.25. Therefore, of it. So here, HTL dot j omega is equal to k over j omega t plus 1. So when omega is equal to 0, HTL dot j0 will be equal to k, of which the magnitude is equal to k, and the phase of HTL dot j0 is equal to 0. When omega is equal to 0.25, HTL dot j 0.25 is equal to k over j 0.25t plus 1, and the magnitude of HTL dot j 0.25 is equal to k over square root of 0.25t squared plus 1, and the phase of HTL dot j 0.25 is equal to the phase of k minus the phase of the denominator, which is 0 minus arctangent 0.25t over 1. Okay, so when we have a complex value alpha plus j beta, the corresponding phase of it will be arctangent beta over alpha. Okay, so here the phase of it is arctangent minus arctangent 0.25t over 1. So as a result, we can write out the expression for yt. So for yt, the corresponding expression will be 0.4 multiplied by k plus 2 multiplied by k over square root of 0.25t squared plus 1 multiplied by sine 0.25t minus arctangent 0.25t over 1, and then multiplied by ut. Put equal to 2 plus 8 sine 0.25t minus 2.574 multiplied by ut. So here we are trying to find the values of k and t. So if we compare this expression with this expression here, which is equation 1 and equation 2, if we compare equation 1 and equation 2, so this term should be equal to this term here, which means we will have 0.4 times k is equal to 2. Then we will have k equal to 5. And then we also have 2k over square root of 0.25t squared plus 1, it is equal to 8. So then we will be able to know that t is equal to 3. Okay, so now we proceed to look at question 4. At steady state, yt is equal to 5 plus 4 times cosine 3t plus 0.3142. It is the phase of HTL dot j025 is equal to the phase of k minus the phase of the denominator, which is 0 minus arctangent 0.25t over 1. Okay, so when we have a okay, so here the phase of it is arctangent minus arctangent 0.25t over 1. So as a result, we can write out the expression for yt. So for yt, the corresponding expression will be 0.4 multiplied by k plus 2 multiplied by k over square root of 0.25t squared plus 1 multiplied by sine 0.25t minus arctangent 0.25t over 1. And then multiply by ut. Put equal to 2 plus 8 sine 0.25t minus 2.574 multiplied by ut. So here we are trying to find the values of k and t. So if we compare this expression with this expression here, which is equation 1 and equation 2, if we compare equation 1 and equation 2, so this term should be equal to this term here, which means we will have 0.4 times k is equal to 2. Then we will have k equal to 5. And then we also have 2k over square root of 0.25t squared plus 1, it is equal to 8. So then we will be able to know that t is equal to 3. Okay, so now we proceed to look at question 4. At steady state, yt is equal to 5 plus 4 times cosine 3t plus 0.3142. It is the output of a first order system of which the transfer function is given by 20 over s plus 4. Derive the corresponding input. Okay, so for the steady state response, if we are trying to use the input to derive the output, then we will have the multiplication in magnitude and addition in phase. If we are trying to use the output to derive the input, then we will have the division in magnitude. So here, this expression should be multiplied by ut. Okay, so we write the expression of yt. It is 5 plus multiplied by ut, and then we have two frequency components. For the first term, omega is equal to 0. For the second term, omega is equal to 3. So we need to find out htl.j0. First, we write out the frequency response. It is equal to 20 over j omega plus 4. Okay, so htl.j0 will be equal to 20 over 4, which is equal to 5. the magnitude is equal to 5, and the phase of HTL.J0 is equal to 0. Then we have HTL.J3. It is equal to 20 over 3J plus 4. The magnitude of HTL.J3 is equal to 20 over 5, which is equal to 4. And then the phase of HTL.J3, it is equal to minus arctangent 3 over 4, which is equal to minus 0.6435. Then we can derive the corresponding input. So the corresponding input will be 5 divided by the magnitude of HTL.J0, which is 5, and then plus 4 divided by the magnitude of HTL.J3, which is 4, and multiply by cosine 3t plus 0.3142 minus the phase of HTL.3j, which is minus 0.6435. Okay, and then multiply by ut. So here we will have 1 plus cosine 3t plus 0.9577, and then multiply by ut. So we have here, it should be noted that we have done the division in magnitude and subtraction in phase. Okay, so now let's proceed to the last question of tutorial 6. A car suspension system and a very simplified version of the system are shown in figure 5a and b. The transfer function of the simplified car suspension system is given by this expression, where we have xos divided by xs. It is equal to bs plus k over ms squared plus bs plus k. Suppose for a car m is equal to 4, k is equal to 1, b is equal to 1, is traveling on a road that has speed reducing stripes, and the input to the simplified car suspension system xit may be modeled by the periodic square wave of frequency omega equal to 1 radians per second, as shown in figure 5c. So now we need to derive the output of it. Okay, so here again it is a steady state response question. So first let's write out the transfer function of the system. So the transfer function of the system here is equal to s plus 1 divided by 4s squared divided by 4s squared plus s plus 1. And then we have the frequency response, which is HTL dot j omega is equal to j omega plus 1 over minus 4 omega squared plus j omega plus 1. Okay, therefore, for xit, we have different frequency components. We have omega equal to 1, 3, and 5, and so on. Okay, so first let's consider the case when omega is equal to 1. So when omega is equal to 1, in this case, we will have 1 plus 1j over minus 3 plus j. And the magnitude of HTL.J1, is equal to 0.4472. And the phase of HTL.J1 is equal to minus 2.0344. Then we have HTL.J3. It is equal to 3j plus 1 over minus 4 times 9 is 36. 36 plus 1 minus 35 plus 3j. So in this case, the corresponding magnitude of HTL.J3 will be equal to 0.09, and the phase of HTL.3j is equal to minus 1.807. And then we look at HTL.J5. It is equal to 5j plus 1 divided by minus 99 plus 5j. Okay, so in this case, the magnitude of HTL.J5 is equal to 0.0514, and the phase of HTL.J5 is equal to minus 1.7177. As a result, we will be able to write out the steady state output. So it is equal to 4 over pi divided by 4 over pi multiplied by 0.4472 times sine t minus 2.0344 plus 1 over 3 multiplied by 0.09 times sine 3t minus 1.807, and then plus 1 over 5 multiplied by 0.0514 times sine 5t minus 1.7177, and so on. As a result, it is equal to 0.5694 times sine t minus 2.0344 plus 0.0382 multiplied by sine 3t minus 1.807, plus 0.0131 multiplied by sine 5t minus 1.7177, and so on. Okay, so that's all for tutorial 6. Now I will proceed to talk about the first two questions in tutorial 7. Okay, so in tutorial 7, consider the cascade LTI system HTL equal to 3s multiplied by 2s plus 1 multiplied by 0.6s plus plus 3 to the power of 2 over 4s squared plus 10s plus 4 times 2s squared plus 8s plus 12.5 times 2s plus 3 to the power of 2. So we need to express it in terms of the DC gain integrator, differentiator, zero factor, and pole factor. Okay, so now let's do it. So in Q1, question A. Okay, so we are trying to rewrite the transfer function. So here we will have 3s multiplied by 2. Sorry, we are trying to rewrite the transfer function. So here we will have HTL.s equal to 3s multiplied by s over 0.5 plus 1 multiplied by 3 square times s over 5 plus 1 square, and then divided by 4 multiplied by s squared plus 2.5s plus 1 multiplied by 2 times s squared plus 4s plus 6.25 multiplied by 3 square times s over 1.5 plus 1 square. Okay, so here we will have 3 multiplied by 9 over, so here 3 square can be cancelled, and then we will have 3 over 8 times s multiplied by s over 0.5 plus 1 multiplied by s over 5 plus 1 square, and then divided by, for this term we can write it as s plus 2 multiplied by s plus 0.5, and then for this term, since the poles are complex valued, so we will leave it like that. So we will have s squared plus 4s plus 6.25, and then the last term is s over 1.5 plus 1 square. And then here, so the first two terms here, we can divide the first term by 2. So this term can be s over 2 plus 1. And the second term, I will divide it by 0.5. So I will have s over 0.5 plus 1. Okay, so I will have s over 0.5 plus 1. And then I multiply here by 2 and 0.5. 2 times 0.5 is 1, so no need to write it. So now I'm going to observe the numerator and the denominator. I find that this term and this term can be cancelled. Okay, so as a result, I will have the differentiator multiplied by s over 5 plus 1 square, which is 2 zero factors, multiplied by 1 over s over 2 plus 1 multiplied by, so here can be written as 6.25 over s squared plus 4s plus 6.25, and then multiplied by 1 over s over 1.5 plus 1 square, and then I have 3 over 8 multiplied by 1 over 6.25. Okay, so in the last step, I will have 3 over 50 multiplied by s over 5 plus 1 square multiplied by 1 over s over 2 plus 1 multiplied by 6.25 over s squared plus 4s plus 6.25, and then multiply by 1 over s over 1.5 plus 1 squared. Okay, so this is the differentiator, double zero factors, cofactor, second order factor, and double cofactors. So in question B, we need to determine how many zeros and poles are there in HTL.S. So the number of poles, we have 1 pole here, 2 pole here, and 2 pole here. So we will have 5 poles in total. And the number of zeros, we have 1 0 here, 2 0 here. So we have 3 zeros in total. And then in question C, we need to determine the high frequency and low frequency asymptotic slopes. Okay. So for high frequency, we will have the number of poles minus the number of zeros multiplied by minus 20 dB per decade. So we will have 5 minus 3 multiplied by minus 20 dB per decade. As a result, it is equal to minus 40 dB per decade. And then at high low frequency, we will have the number of the integrators minus the number of the differentiators multiplied by minus 20 dB per decade. So here the number of integrators we do not have is 0, and the number of degrees, which is minus 180 degrees. At low frequency, we will have the number of poles minus the number of zeros. Oh, sorry, at low frequency, we will have the number of integrators. So now we can proceed to question 2. Okay, so we need to draw the body magnitude and phase plots for the system H1 T.S and H2 T.S. First, let's look at H1 T.S. So in H1 T.S, we have a cofactor and a differentiator. So in this case, we will have 1 over S over 100 plus 1 multiplied by 1 over 10 times S. So I'm going to plot the body diagram for the differentiator and the cofactor separately and then add them up. Okay, so let's first plot the body diagram for the differentiator. So for the differentiator, the magnitude plot will be a straight line with slope equal to plus 20 dB per decade, and it will pass to the point 10, 0. Okay, so it will pass to the point 10, 0, which is here, and the slope will be equal to plus 20 dB per decade. The phase plot for the differentiator is always equal to plus 0. Okay, so it will pass to the point 10, 0, which is here, and the slope will be equal to plus 20 dB per decade. The phase plot for the differentiator is always equal to plus 90 degrees. And then let's look at the cofactor. So for the cofactor, I use the green color. At low frequency, the magnitude of the cofactor is equal to 0 dB. And then there will be a slope change at 100 radians per second. When the frequency is larger than 100 radians per second, the slope of it will be equal to minus 20 dB per decade. And then for the phase of it, when the angular frequency is less than 100 over 10, which means the angular frequency is less than 10, the phase will be equal to 0 degrees. And when the angular frequency is larger than 1000, the phase will be equal to minus 90 degrees. Okay. In between, we can connect these 2 points. And now I can do the summation. I will use the black color. So I partition the frequency domain into different segments and then do the summation. So this is the final magnitude plot. And then this is the final phase plot. Now we can proceed to see H2 tilde S. So for H2 tilde S, the expression as S over 100 plus 1 multiplied by 10 multiplied by 1 over S. So we have an integrator and a zero factor. First, let's look at the integrator. So for this integrator, I will use the red color. In the magnitude plot, it will be a straight line with slope equal to minus 20 dB per decade, and it will pass to the point 10, 0. So it will pass to the point 10, 0 with slope equal to minus 20 dB per decade. And then the phase of it is always equal to minus 90 degrees. And then for this zero factor, I will use the green color. So when the frequency is very low, the magnitude is equal to 0 dB. And there will be a slope change at omega equal to 100. When omega is larger than 100, the slope of it is equal to plus 20 dB per decade. And then for the phase of it, when the angular frequency is less than 10, the phase of it is equal to 0 degrees. When the angular frequency is larger than 1000, the phase of it is equal to 90 degrees. And in between, I can connect these 2 points. Now I'm going to plot the final magnitude plot and phase plot. So I'm going to partition the frequency domain to different segments here, and then do the summation. Okay. So that's all for the first 2 questions of tutorial 7. Okay. Thank you for listening to the class. Good afternoon, everyone. So today we are going to talk about tutorial 7 and tutorial 8. So I will start earlier in order to have enough time for each question. Okay, so last time we have covered Q1 and Q2 in tutorial 7. So now we start with Q3. Before we talk about Q3, let's do a quick review about the basic systems we have learned in the lectures. So the first one is KDC, which is called the DC gain. The second one is the differentiator, which is KD multiplied by S. The third one is the integrator, which is KI over S. The fourth one is the zero factor, which is S over Zm plus 1. And the fifth one is the pole factor, which is 1 divided by S over Pn plus 1. And the last one is the second order factor, which is omega n squared divided by S squared plus 2 zeta omega ns plus omega n squared. Okay, so for Q3, we need to express the transfer function in terms of the basic systems. Okay, so now let's look at the transfer function of the system here. So here we have htr.s, which is equal to, so if we look at zero factor, order factor, first I will write the denominator. Then in the numerator, we'll have to multiply 1 over 0.2. Does it make sense? Okay, so that's 25. Therefore, we have three subsystems. The first subsystem is the DC gain. The second subsystem is the zero factor. The third subsystem is the second order factor. So now I need to find the DC gain in dB. First, I can see that the DC gain, it should be equal to this factor here, which is equal to 10, and 10 is equal to 20 times log 10 of 10, which dB, which is equal to 20 dB. Okay, so this is the DC gain value, 25. So for the y, so in order to determine the system whether it's larger than 0, less than 1, therefore it is underdamped. Okay, and now we need to draw the body magnitude and phase plots for the system using different colors. So it should be 0 degrees at low frequency located at here, and then the slope change will be equal to minus 20 dB, and here equal. So this is the magnitude plot of the zero factor. Now we look at the phase plot of the zero factor. So when the frequency is very low, the phase of the zero factor will be is less than 5. It is equal to 0. 500 is here. There will be a slope change at omega equal to 5, which is 2, 3, 4, 5 here. Very hard to plot. 0.5, it is equal to 0 degrees. So 0.5 is here. 0.5 is here. And when the frequency is larger than 50, it is equal to minus 180 degrees. And 50 is here. And in between, we can connect these 2 points. Okay. And now in the last step, we need to do the summation. So we will partition the frequency domain. From 0 degrees to minus 90 degrees. And in the third segment, it will decrease from minus 90 degrees to minus 135 degrees. And in the fourth segment, it will increase from minus 135 degrees to minus 90 degrees. And in the last segment, the phase will be the same, which is equal to minus 90 degrees. see that the magnitude is equal to minus 40 dB and the slope is equal to 0. So it means that we will have a DC gain, right? We will have KDC. And how do we know the value of KDC? So we will have 20 times log 10 of KDC. It is equal to minus 40 dB per decade at omega equal to 0.3 radians per second. So if the slope change is equal to minus 20 dB per decade, it means that we have a pole factor. So the pole factor will be 1 divided by S over Pn plus 1. Because the slope change happens at omega equal, which is here, the third slope change of minus 20 dB per decade at omega equal to 50. Since the slope change here is negative and it is equal to minus 20 dB per decade, therefore we will have a pole factor. So the pole factor is represented by 1 over S over Pn plus 1. And since the slope change is happening at omega equal to 50, therefore over 0.3 plus 1 multiplied by S over 6 plus 1 square multiplied by 1 over S over 50 plus 1 and multiplied by 1 over S over 200 plus 1 square. Integrator. So we will have a integrator, yes, ki over s. And we need to find the value of ki. So we can see this straight line here, it will cut this point. Since it cut this point here, this point is corresponding to 0.1, 0.2, 0.1, 0.2, 0.4, okay? So it cut the point 0.4, 20 dB. So we will have 20 times log 10 of ki over 0.4 is equal to 20 dB. So we have ki over 0.4 is equal to 1. So ki is equal to 0.4. And then we look at the slope change. So the first slope change happens here. Oh, very hard to see. So the first slope change happens here. So it is equal to 0.2, 0.3, 0.4, 0.5, 0.6, 0.8, 0.9. Okay, it happens at omega equal to 0.9, and the slope change is equal to plus 20 dB per decade. So we have slope change plus 20 dB per decade at omega equal to, is it 0.8 or 0.9? Oh, 0.8, sorry. Omega equal to 0.8. So here, since the slope change is positive, so we will have a zero factor. So the zero factor will be S over 0.8 plus 1. And then we look at the second slope change, which is here. Okay. The second slope change, it is equal to minus 20 dB per decade at omega equal to 8. Since the slope change is equal to minus 20 dB per decade, therefore we will have a pole factor, which is 1 over S over 8 plus 1. And then we look at the third slope change, which is here. So the third slope change, it is equal to minus 20 dB per decade at omega equal to 50. Since the slope change is negative and is equal to minus 20 dB per decade, therefore we will also have a pole factor, which is 1 over S over 50 plus 1. And then the final transfer function, htl.s, it will be equal to 0.4 over S multiplied by S over 0.8 plus 1 multiplied by 1 over S over 8 plus 1 multiplied by 1 over S over 50 plus 1. Minus 20 or minus 40. Oh, you mean from the graph, how can I know it's minus 20 or minus 40? So in general, we only have slopes equal to minus 40, minus 20, 0, 20, 40, or minus 60 plus 60. So you can observe the value change in 1 decade. So let's say from this point, if you extend this line here to this point, you can see it decrease by about 20 dB. So I can say that the slope is equal to minus 20 dB per decade. And then for this one, so in 1 decade, decreased from this value here to this value here. So it decreased 40 dB. So I can say that the slope of it is equal to minus 40 dB per decade. So we need to describe the behavior of the system at very low frequency and at very high frequency. In fact, we can observe it from this graph here. So at very low frequency, it is like the integrator. At very low frequency, it is like the integrator. This is the graph of the integrator, right? The slope here is corresponding to the integrator. And then at very high frequency, it is corresponding to this straight line here. We can see that the slope of it is equal to minus 40 dB per decade. It means that we will have two integrators. So at very low frequency, we have one integrator. At very high frequency, we have two integrators. But we can derive it using maths. Okay, so we can see that when omega is much less than 0.8, if omega is much less than 0.8 radians per second, HTL.S is approximately equal to, so we look at the first term cannot be approximated, it's still equal to 0.4 over S. And then in the second term, since S is much less than 0.8, so it can be approximated by 1, because the first term will be much less than 1. So it is approximated by 1. And then we look at the third term, since omega is much less than 0.8, so the first term in the denominator will be much less than 1, so the third term can be approximated by 1. And then for the first term, since S is much less than 0.8, so the first term in the denominator will also be much less than 1, so the fourth term can be approximated by 1. As a result, HTL.S can be approximated by 0.4 over S, so it is an integrator. And now we look at the case when omega is much larger than 5 radians per second. When omega is much larger than 5 radians per second, the transfer function is approximated by, for the first term, we cannot change the expression, so it is still 0.4 over S. For the second term, since omega is much larger than 50, so S over 0.8 is much larger than 1, so it can be approximated by S over 0.8. And then for the third term, since S over 8 will be much larger than 1, so the third term can be approximated by 1 over S over 8. And then for the last term, since S over 50 is much larger than 1, so the last term can be approximated by 1 over S over 50. And as a result, the transfer function can be approximated by 2000 over S squared. S over 8 plus 1 multiplied by 1 over S over 50. Since the slope change is positive, so we will have a zero factor. So the zero factor will be S over 0.8 plus 1. And then we look at the second slope change, which is here. Okay. The second slope change, it is equal to minus 20 dB per decade, be equal to 0.4 over S. So here, okay, if there is no question, let's look at the last question. The Bode magnitude plot for the system HBTL.S is equal to K multiplied by S plus A, S plus B, S plus C divided by S plus D times S squared plus 2 theta omega n S plus omega n squared. It is shown below. Find the values of K, A, B, C, D, and omega n. Okay, so here we need to derive the transfer function according to the magnitude plot. First, let's look at the low frequency asymptote. At low frequency, we can see that the slope is equal to plus 20 dB per decade. Since the slope is positive and it is equal to plus 20 dB per decade, therefore we will have a zero factor. So we will have S over Zn plus 1, and we can see that this straight line cut this point here. So it cuts the point 0.2 minus 20 dB. So we will have, oh sorry, it's not zero factor. I made a mistake. Since the slope is positive, so we will have a differentiator which is Kd multiplied. And then we proceed to look at the slope change. We can see we have the first slope change here. So the slope change is equal to minus 20 dB per decade, and it is located at omega equal to 4. Since the slope change is negative, so we will have a pole factor, which is 1 over S over Pn plus 1. And since the slope change is at omega equal to 4, so we will have 1 over S over 4 plus 1. And then we look at the second slope change. The second slope change is here. The slope change is equal to minus 40 dB per decade, and it is located at omega equal to 30. Since we have a resonance here, therefore it cannot be double whole factors, it can only be a second order factor. So the corresponding transfer function will be omega n divided by s squared plus 2 theta omega n s plus omega n squared. And since the slope change is at omega equal to 30, therefore the undamped natural frequency will be equal to 30. So we will have 900 divided by s squared plus 60 theta s plus 900. So when you see the resonance, it can only be the second order factor. And then we look at the last slope change, which is located at omega equal to 200. Okay, so we have the last slope change, which is plus 40 dB per decade at omega equal to 200. Since the slope change is positive and it is equal to plus 40 dB per decade, therefore we will have two identical zero factors, which is s over zm plus 1 square, and it is equal to s over 200 plus 1 square. So we can multiply them together. We will have htl.s equal to 0.5s multiplied by 1 over s over 4 plus 1 multiplied by 900 over s squared plus 60 theta s plus 900, and then multiplied by s over 200 plus 1 square. And then we need to compare this expression with the original expression. So we need to rewrite it. 0.5s multiplied by 4 over s plus 4 multiplied by 900 over s squared plus 60 theta s plus 900. And then the last term will be 1 over 200 square multiplied by s plus 200 square. Then the final expression we have will be 0.045 multiplied by s plus 200 square, and then multiplied by 1 over s plus 4 multiplied by 1 over s squared plus 60 theta s plus 900. And then we will be able to find the value of k, a, b, c, d, and omega n. So we can find that k is equal to 0.045, a is equal to 0, b is equal to c is equal to 200, and omega n is equal to 30. Oh, sorry, d is equal to 4, yeah. Questions about tutorial 7? No questions. Okay, so now we can talk about tutorial 8. If you see resonance, it should be a second order factor. If you don't see resonance, it depends on the question. If we tell you the poles are real, then it should be real factors. If the poles are real, then we do not have second order factor. Yeah. Okay, so now we proceed to tutorial 8. In tutorial 8, a signal xt, which is equal to 2 to the power of 1 minus